Logarithmic Functions, Chapter 5, Section 4. Logarithmic function with base a. The logarithmic function with base a, where a is greater than 0 and a is not equal to 1, is denoted by y is equal to log base a of x, read as y is the logarithm with base a of x, and is defined by y is equal to log base a of x if and only if x is equal to a to the y. Notice we're seeing a transformation here. Y is equal to log base a of x if and only if x is equal to a to the y. Now remember, that's essentially a to the y is equal to x. That's an exponential function. So logarithmic functions and exponential functions are related to each other. Notice they both have the same base here, log base a of x, and you've got a to the y equal to x, right? A is the base. So what happens is, as you go from a log base a of x equal to y to x equal to a to the y, the base stays the same, and you kind of just swap the location of the x and y and drop the log. Now the domain is from 0 to infinity, and the range is from negative infinity to positive infinity. Obviously, both of those exclusive. So let's go through some examples of converting logarithms and exponential functions. So here I've got a table with a number of logarithmic equations and exponential equations, and we're just going to go and convert them. So we got log base f of g is equal to h. Now to convert that to an exponential function, we're just going to take the base f and raise it to what was on the other side of the equation, the h, and set that equal to g. So it's f to the h is equal to g. Now, the next one, I gave you the exponential function. T to the n is equal to r. So that's going to be log base t of r is equal to n. Notice the base stayed as the base, and then we just swap the other two. Now I have log base 5 of 125 is equal to 3. So I have 5 to the 3 is equal to 125. And here I have 2 to the 8 is equal to 256. So that's log base 2 of 256 is equal to 8. Bases stay the same, swap the other two values. Moves you back and forth between logarithmic functions and exponential functions. So what are some properties of logarithmic function? If you have f of x is equal to log base a of x, where a is not equal to 1. The domain is the set of all positive real numbers, and the range is the set of all real numbers. The x-intercept of the graph is 1. There is no y-intercept. The y-axis, x equal to 0, is a vertical asymptote of the graph. A logarithmic function is decreasing if a is between 0 and 1, and is increasing if a is greater than 1. The graph of f contains the points 1, 0, a1, and 1 over a, negative 1. Now, if you look at this, what we're seeing at this point, this should look familiar but different. X-intercept of the graph is 1. There is no y-intercept. When we were dealing with exponents, the y-intercept of the graph was 1. There was no x-intercept. For logarithms, y-axis is a vertical asymptote. For exponents, the x-axis was a horizontal asymptote. Now, the increasing and decreasing, that stays the same with the a. The graph of f contains the points 1, 0, a1, and 1 over a, negative 1. Well, for an exponential function, it included the point 0, 1, 1a, and negative 1, 1 over a. Are we seeing something here? It seems like everything's opposite. Well, what does that mean if it's opposite? Well, doesn't that make them inverses, inverse functions? The graph of f is smooth and continuous with no corners or gaps. So graphing a logarithmic function, that should say a logarithmic function, not an logarithmic function. So f of x is equal to log base 4 of x. If I want to graph that, well, the first thing I have to do is I have to look at, okay, the base is 4, so a is equal to 4, which is greater than 1, so it's going to be increasing. We know that we're going to have the following points. Well, these are just the opposite of what we had before. So 1 over a, negative 1. So that's 1/4, negative 1. 1, 0, and a1 or 4, 1. So we've got the points 1 over 4, negative 1, 1, 0, and 4, 1. And we know that the y-axis is an asymptote. So now if we graph those 3 points and put a curve through it, we see that we get this function. Now, if we look at this and we think about what our exponential function looked like, and we look at what happened with the inputs and outputs, these being inverse functions, this is really the graph of 4 to the x, y equals 4 to the x, reflected over the line y equal to x. Remember, we said we could get those graphically, we could get the inverse graphically, or in this case, we've also done it with the points. We've done it algebraically, just flipping those. So we can graph it, and it graphs the same way. And as I said with exponential functions, if you have a logarithmic function, the same transforms happen. If I were to put a 3 in front of this, 3 times the log of log base 4 of x, then that would multiply all of the y values by 3. So instead of having 1/4 negative 1, we'd have 1/4 negative 3. We'd still have 1, 0. But then instead of having 4, 1, we'd have 4, 3. So all the things would happen. If I added a -2 to the end, it would go down by 2. If I had it log base 4 of 5x, then it would go through it. It would go through the x-axis 5 times faster. So instead of having 1, 0, we'd have 1/5 0, etc. Logarithmic function with base e. So when you have a logarithmic function with base e, it's denoted by y equal to ln x, which is read as y is the natural logarithm of x, or we know it as the natural log of x. And is defined by y equals the natural log of x if and only if x is equal to e to the y. So the natural log of x is the inverse of the exponential function e to the y. Okay, so the natural log. So anytime you see this ln of something, it's saying take the natural log. It's basically log base e of x. So your bases become e. The domains from 0 to infinity exclusive and ranges from negative infinity to positive infinity. Now, if you have a logarithmic function with base 10, we can denote that by y equals log of x. Now, when you have that, when you have a log base 10, that's known as the common log of x. So if you think about when you take the square root of something, we don't write the 2 for the index. If we had the cubed root, the fourth root, we write the index there. Same thing with log. If you do not have a base written, it is assumed that it is common log, which is base 10. So then y equals log of x if and only if x is equal to 10 to the y. Or you could say log is the common, y is the common log of x if and only if x is equal to 10 to the y. Domain again from being from 0 to infinity exclusive, range being from negative infinity to positive infinity. So we can see these relationships, and we also see that there are specific cases. And if you look on your calculator, you'll see that there's a log key and there's a natural log key. Or if you have a graphing calculator, you may need to go into your functions. And then with that case, depending on your calculator, you may actually have a log base function, so you can actually put in the choose your base. But your basic scientific calculators will only have log and natural log.